In this presentation, I will demonstrate the procedures for determining thermodynamic properties of pure substances from tables of property data. Thermodynamics properties are frequently presented in the form of tables. The steam tables will be used to demonstrate the use of thermodynamic property tables. My explanation will be based on a TV diagram. For each substance, the thermodynamic properties are listed in more than one table. A separate table is prepared for each interest region, such as the superheated vapor, compressed liquid, and saturated mixture regions. Property tables are given in the appendix in both SI and English units. For instance, tables A4 until A7 list the thermodynamic properties for water. I will begin the demonstration by introducing table A4. This table tabulates the properties of saturated liquid and saturated vapor for water. The subscript F denotes a saturated liquid's properties. States that rest along this line exist in the saturated liquid phase. Thus, the state's properties can be obtained from the related F values in the properties table. Other properties than specific volumes, such as internal energy, enthalpy, and entropy, behave similarly on their respective property diagrams. The subscript G denotes the properties of saturated vapor. States that rest along the saturated vapor line exist in the saturated vapor phase. Therefore, the state's properties can be obtained from the related G values in the properties table. Another subscript commonly used is Fg, which denotes the difference between the saturated vapor and saturated liquid values of the same property. It can be shortened through the following equations. For the specific volume, the difference can be determined by subtracting saturated vapor and saturated liquid values at a given state. How to determine saturated liquid and saturated vapor states? Generally, we obtain thermodynamic properties of both states in tables A4 and A5. Both tables give the same information. The only difference is that table A4 properties are listed under temperature and table A5 under pressure. Therefore, it is more convenient to use table A4 when the temperature is given and table A5 when pressure is given. A rigid tank contains 50 kg of saturated liquid water at 90 degrees Celsius. The tank's pressure and volume are to be determined inside the rigid tank. To provide a systematic solution, let us use this rule of thumb. First, we sketch a saturation line on a suitable property diagram that includes all the necessary given properties, such as substance temperature and pressure. Second, we establish each axis of the diagram based on the given information. For instance, example 3.1 provides the saturated liquid water temperature and volume. Therefore, we could sketch a TV diagram. Third, on a TV diagram, we draw the corresponding saturation pressure constant line of the water temperature of 90 degrees Celsius. The pressure value can be obtained in table A4 because we are given a temperature value. At temperature of 90 degrees Celsius, the corresponding pressure value is 70.183 kilopascals. Fourth, we determine the phase of the state through the property diagram that we had sketched earlier. Please note that the phase of any states can only be determined through the state postulate. It means we must first establish two independent intensive properties before determining the phase of the state. However, example 3.1 has provided the state's phase, that is saturated liquid. Therefore, we can straightaway indicate the state on the TV diagram, as demonstrated. Fifth, once the state phase is defined, we can straightaway lead to appropriate property tables to obtain other states' properties. Therefore, based on example 3.1, we can determine the corresponding specific volume of the given temperature of 90 degrees Celsius in table A4, as shown. Now, we can determine the pressure and volume of the tank. Because we have already known the phase of the state. Since the state lies on the saturation pressure constant line, the tank pressure is the saturation pressure at 90 degrees Celsius, as specified. The total volume of the tank is the product of mass and specific volume. The specific volume of the saturated liquid at 90 degrees Celsius is 0.001036 cubic meters per kilogram, obtained in table A4. The saturated liquid mass is given 50 kilograms. Therefore, the total volume of the tank becomes 0.0518 cubic meters. Now let us discuss example 3.3. The example involves a piston cylinder device containing 200 grams of saturated liquid water. The saturated liquid water is vaporized at constant pressure. The piston cylinder system undergoes a constant pressure process where the initial state is in the saturated liquid phase and the final state is in the saturated vapor phase. The volume change and the energy transferred is to be determined. To solve this example, the 5 rules of thumb will be adopted. First, we sketch a saturation line on a suitable property diagram that includes all the necessary given properties, such as temperature, pressure, or specific volumes. Second, We define each axis of the diagram based on the information given. For example, 3.3, it provides the saturated liquid water pressure, and we are asked to determine the volume of the system. Therefore, we sketch a PV diagram. Third, on the PV diagram, the corresponding saturation temperature constant line of the water at 100 kilopascals is illustrated. The corresponding saturation temperature of the given pressure is 99.61 degrees Celsius, attained in table A5. We must specify the saturation temperature value on the saturation temperature constant line as demonstrated. Fourth, determine the phases of both states based on the property diagram. As I mentioned earlier, the phase of any states can only be determined through the state postulate. The state postulate means we must first determine two intensive properties for each state, such as temperature, pressure. For example, 3.3, since we are given the system's pressure and the system undergoes a constant pressure process, therefore, the pressure of each state is known. Specifically, 100 kilopascals. However, example 3.3 has also given the phase for each state. The initial state is in a saturated liquid phase and the final state is in a saturated vapor phase. Each state's location on the PV diagram is demonstrated. A process path is sketched to connect the two states. Fifth, once both states' phases are defined, we can straightaway refer to appropriate property tables to obtain other states' properties, such as specific volumes. For example 3.3, we can determine the corresponding specific volumes of both states at the given pressure of 100 kilopascals from table A5, as demonstrated. The volume change is a product of the mass of the saturated liquid water and the specific volume of the vaporization process. Therefore, the total volume change during a vaporization process can be determined through the following analysis. The specific volume of the vaporization process is the difference between the specific volume of the saturated vapor and the specific volume of the saturated liquid, or V subscript G minus V subscript F. Thus, the volume change is 0.3386 cubic meters. The amount of energy needed is determined by multiplying the mass of the saturated liquid water with the enthalpy of vaporization at the given pressure. A new property called the enthalpy of vaporization is introduced. It is denoted as H subscript Fg. It is defined as energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. It decreases as the temperature or pressure increases and becomes zero at the critical point. It can be determined through appropriate properties table. For instance, based on table A5, at pressure of 100 kilopascals, the corresponding HFG is 2257.5 kilojoule per kilogram. Therefore, the amount of energy transferred is 551.1 kilojoules.